Good day, everybody, and welcome to this new sub-chapter in our Calculus 1 course. This sub-chapter is entitled Rules of Derivatives, and today we'll do part 1 of it. So, before we go on, let's just remind ourselves. So, let us remind ourselves that basically the derivative is obtained through mainly one formula, right? Of course, we know a counterpart to that, but the one we use the most often is this one. Over h, right? We also have the other version of this, which we have used at times. It's slightly less utilized, if I can say. Limit as x approaches a of f of x minus f of a over x minus a. This one here already includes the point a in it. So whenever we want a derivative and we're given, say, at x is equal to 1, then it might be a good idea to try that. Otherwise, this little guy is our formula of reference. Okay, we know this, we've been practicing this plenty, and we have been able to calculate several derivatives using it. Good. Now what we want to do today is actually use this to find shortcuts to the derivative of well-known formula. For example, number 1, consider f of x is equal to c, where c is a constant. My question would be, what is f prime of x? What is f prime of x in this case? Okay? So, in other words, if I have a constant, like a number like 7, and I want to figure out its derivative, of course, I can use this, right? And I will. And I will, and I will, and I will. So f prime is the limit as h goes to 0 of... All right, what is this guy? What is f of x? Well, f of x is c. What is f of x plus h? Well, then I need in here to replace x with x plus h. But what will this change to the other side? I mean, if I replace this x with x plus h, will I replace anything on the right-hand side that is different from what's already there? The answer is no. This actually happens to be simply the limit as h goes to 0 of c minus c, so 0 over h. Now, you remember that h approaching 0 also means h is not 0. So when I'm going to do what I'm going to do here, is this. I'm going to make that equal to 0. Why? Because this is actually not 0 over 0. It's 0 over 0.1 or 0.01. And that, of course, is 0. And here lies our first rule of derivatives. Conclusion. If f of x is a constant, then always, we can actually use this as a shortcut if you want, then f prime is 0 all the time. We just proved it. So the derivative, in other words, in perhaps a more like shortened notation, something perhaps we can box, what we're saying here is that if I have a constant and I take its derivative, like the derivative of 7, for example, what will that give me? The derivative of a constant has been proven to be 0. And that is rule number 1. That is rule number 1 of the derivatives. There's a whole list of rules of derivatives. That's why we will devote more than one lecture on this. But you see how this goes, right? It's a simple application of the basic formula. and at the end of it, we get some sort of a rule. Good. Let me erase this and move on to another rule. Let us see if we can perhaps investigate the derivative of another well-known function known as f of x is equal to, good coffee, f of x is equal to x. So rule numéro 2, second rule. This time I would like to investigate this guy. F of x is equal to x. La question, what is the question? Of course, what is f prime of x when f of x is equal to x? And the answer always begins the same way. Yes, limit definition. Limit definition. Now we are, I believe, quite familiar with this. So this time, the function is not a constant. The function is like a straight line with a y-intercept of 0 and a slope of 1. So a straight line right through the origin. All right, so let us see if we replace that in here. What is it that we're going to get? Why don't we replace f of x right away? Because it's easy. Why is it easy? Because it's given. F of x is x. Yay. What is f of x plus h? Well, if I replace this x with x plus h, I'm going to have to replace this x by x plus h as well. So f of x plus h is x plus h. So now what I have is the limit as h goes to 0 of x plus h minus x over h. I'm sure you see a simplification, right? The simplification here is, of course, that and that. And we are suddenly left with this over that. I'm going to cancel the h's, and of course I can do that because I am not canceling 0 and 0. Remember that h approaching 0 also means h is not 0. So this is equal to 1, and there we have it. There we have it. If f of x is equal to x, then f prime of x is equal to what? 1. Here we go. So we can actually write this perhaps like in a way we did for the previous rule number 1. So rule 2, second rule of derivatives. Let us write it with the prime embedded already into it. So the derivative of the function x, right? F of x equals x. The derivative of that function is 1. And that is rule number 2. Good. So I'm going to come up with the third rule, and then having 3 rules together, we'll be able to do some sort of examples. It's a bit early now to try to exemplify this because these rules are very, very simple, as you can see, and they address a very limited class of functions as well. Good. So let's get rid of this and let's move on to a rule 3 that actually will combine somehow the first 2 rules together. So rule numéro 3, third rule. This time I would like to consider the function f of x is equal to cx, where c is a constant. If you read some textbooks, sometimes they replace c with k. Same thing, as long as we have a constant multiplying plane x, we are good to go. Alors, la question, usual, what is the question? What is f prime of x? So the only way we can figure this out is through the limit definition. F prime of x is the limit as h goes to 0. I'm sure you can complete that sentence. Yes, fx plus h minus fx over h. Good. So limit h goes to 0 of, all right, here we go again. I need to replace f of x here. What is f of x? It is given as cx. Now I need to replace f of x plus h. That means that I need to replace this x with what? X plus h. And if I do that, I'm going to have to replace this x also with x plus h. Entonces, this is cx plus h, close the bracket. Okay, well, once again, I didn't mention it before, but as you know, when we start the limit definition, we always start with 0 over 0. We would get that certainly at this stage. You can verify it. And we are going to try to see if we can simplify this a little bit. So, the obvious thing to do here is to expand this bracket. And we're going to get cx plus ch minus cx. And of course, this is gone. So I end up with the limit as h goes to 0 of ch over h. Well, there we go. Another cancellation right here. And I have the limit of a constant. Oh, I haven't seen that in a while. Limit of just c as h goes to 0. So if I cheat on this and I replace h by 0 in here, clearly I have no place to put the h. This is just c. So the conclusion to this is that if f of x is equal to a constant times x, then f prime is simply equal to c. We basically can write this in the following form. So rule number 3, the derivative of c times x is equal to just the constant c. And that is our third rule. So before we go on to the fourth rule, we're going to do two things. I'm going to have a sip of coffee. And maybe you do the same. And we're going to practice a little bit on these guys. So let's get rid of this. And let's see if we can come up with a couple of examples. All right. So, like I said, at this stage, the functions are relatively limited in choices. So perhaps we can attempt something like this. Find the derivative of the following functions. Okay. Now, what could I put down here as an example? Suppose f of x is equal to 7. What is f prime of x? Well, f prime of x is the derivative of 7. And 7 is a constant. There are no x's in here. So the derivative of a constant is 0. And we know this how? By rule 1. So that actually helps us to bypass the limit definition and use the rule to get the answer much more quickly. What about this? F of x is equal to x3 over x2. Uh-oh. Division? I don't think I've seen a rule for division. Would it be possible that I am trying to trick you? Certainly not. I would never do that. This simplifies to what? This simplifies to f of x is equal to x3 over x2 is x1. So f prime of x is the derivative of this. Well, it's a derivative of x. And the derivative of x is 1 by rule 2. Okie dokie. What about something like this? F of x. I should change the name of f of x. I could call it g of x or h of x or whatever. I'll just get used to f of x. Let it be something like, I don't know, 8x. So a constant times x. So f prime is the derivative of 8x. Do you recognize this to be c times x? So this is rule number 3. The derivative of 8 times x, the derivative of c times x is c. So that's 8. And that is true by rule number 3. Okay, one last. Okay, why don't we call it g of x? So g of x is 16x to the 3/2 over 4 root x. What? That is one ugly thing, huh? Yet, what is g prime? Well, before we go to g prime, we should probably try to see if we can simplify this ugly thing, right? So what's g of x? 16 and 4. 16 and 4 is 4. As for the x's, this is x to the 3/2, and this is x to the 1/2, so I shall subtract my exponents, and, well, look at that. How well carved is this problem? Oh my god. X to the 3/2 minus 1/2 is x to the 2/2 is 1. So, in disguise, I was asking you, what is the derivative of 4x? So I can actually say that g of x is now simplified to be 4x. What is g prime? G prime is the derivative of 4x. You recognize once again rule number 3, a constant times x, and that's equal to just a constant. The x is gone. And why is that? That is because of rule number 3. All right, so that gives you like a quick overview of what is going on. Let's move on to rule numéro 4. All right. Rule number 4 is by far the most important in this chapter. Well, there's a couple of important, but that is super important rule. F of x is actually x to the power of n. Genre x to the 3, even x to the 1/2, even x to the -1, right? So x to any power, we can actually show that n is just an element of the real numbers. So you can have even x to the power of root 2. Any number here will do, positive, negative, rational, irrational. So, évidemment, the question remains the same. What is f prime? What is f prime of x? Okay, well here, basically, the limit definition can be used. I'm going to have to actually skip a few steps because there's a lot of algebra involved, and I am not going to hold you responsible either on an assignment or on a test for the derivation of this thing. So f prime, we still have no choice. We still have to go through the limit definition to figure out the general rule for this. F of x over h. Okay, so that's the limit as h goes to 0. And then what do we have here? All right, let us start by what seems to be the easiest. Let us replace, as usual, f of x. It is given. It is x to the n. Now take a second and figure out what is it you're going to put here in the place of f of x plus h. What should go there in the place of x plus h? Well, f of x is here. You want to replace this x with x plus h. So what does that mean? You're going to replace also this x by x plus h. So we have something like this, and that is where, in terms of algebra, this is where things start to go a little complicated. Why? Why do we actually go complicated? Well, first of all, as usual, at this stage of the game, you're going to recognize the 0 over 0, right? But to expand this to an unknown power n is not a simple matter. It's not a simple task. If I know the n, genre, if n is 2, then x plus h to the 2 I can develop, no sweat. If n is even 4, it's going to be longer, but I can actually do x plus h to the 4 by multiplying x plus h by itself 4 times. The problem is I don't know what the power is, it's unknown. And this is where we actually call upon something called a binomial formula thing. Again, you're not responsible to know this, you're not responsible for the derivation of this. I just thought I would actually show it to you. And if you actually want to know a little more about where this comes from, you can actually ask me on Zoom and I will gladly give you the details. But for now, limit as h goes to 0. We're going to develop this baby, x plus h to the n. And we're going to get like a bunch of terms. It's all going to be over h, and of course, it's all going to be in the end minus x to the n, so I put it right there at the end of the line. So now I want to expand this. I'm going to expand this. First of all, I'm going to give it another color since it is actually something that stands out of the expression. So this is x plus h to the n. So if I develop that in green, I'm going to get x to the n plus n x to the n minus 1 h plus a bunch of terms that will actually all contain some sort of an h thingy. This is where kind of a bit of the work has to be filled in through what we have called before the binomial theorem. But like I said, I'm not holding you responsible for this right now. So we're just going to leave it like that. The expansion of this, how this expands, is through a formula that actually involves these terms. For now, this is almost all we need. So let us see if we can advance this a little bit. Do you see a cancellation on this upper line? I see one. It should be here. It should be here. X to the n minus x to the n. All right. Well, that helps a little. And now what I'm going to have is, probably stick to the green here, is n x to the n minus 1h plus a bunch of terms all over h. Now, what I'm not actually telling you here is that all of these terms, all of these remaining terms, all the way down to the very end, they all contain an h. Like, here's the lowdown if you really want to know. This guy contains an h to the 1. The next guy will contain an h to the 2. And then the guy after that will have an h to the 3, and so on and so forth. That's the part that I'm leaving out because it's a bit complicated and we don't have that much time on our hands. So basically what I'm saying is that we can factor out from the top an h. We can factor out from the top an h. And what we're going to get, once we do that, we're going to get here, well, this h will go out, so I'll have n x to the n minus 1 plus, like I said, a bunch of terms that include this actually includes an h. Why does that matter that they include an h? Well, first of all, we're going to cancel those, right? And now we are going to cheat. Since I'm going to replace h by 0 and these are gone, and because all of these guys here contain an h, when I replace h by 0, all of this here goes to 0. All of that jazz will all go to 0. Why? Because once again, it contains an h. So what do I get? I know I'm asking for like a big leap of faith on your part here, because I haven't shown why all these terms include an h, but we'll have to take that for granted for now. So if all of this goes to 0 and my h's are gone, I am left with n x to the n minus 1. And that means that we now have rule number 4. Unfortunately, I do not have that much room to put it, so I will go over here if you allow me. I don't like to do that, but it's a small whiteboard. So basically now, you know what, I'm not going to do that. It's going to mess up the board, really. I'm just going to have to recopy something on the next whiteboard. So just erase this thing here, and we'll just put it here. All right. Alors, f of x is equal to x to the n. So now we have that f prime of x is the very, very last line we had before I erased, n x to the n minus 1. Or, if we want to write this in the other notation, rule 4 reads the derivative of x to the n. We can write it like this with the apostrophe to mean the derivative. And this is n x to the n minus 1. And we call this rule number 4. Let me show you a couple of examples on how this works. Example. F of x is equal to x to the 3. What is f prime? Well, this is x to the n. You see? You see the pattern? X to a power, x to a power. What's the derivative? I'm not going to go through limit blah blah blah. I have a rule now, and this rule tells me that I can take that exponent n, bring it in front. I can take that exponent n, bring it in front, and then I can subtract 1 from the exponent. And 3x squared is what you're going to get. If you did the limit definition on this, you would have f of x plus h minus f of x over h. You would have to expand x plus h cubed, simplifications, blah, blah, blah. And in the end, the only thing that would be left is 3x squared. You can see that this is actually an amazing shortcut. Okay, what about f of x is equal to root x? What is the derivative of that? Well, f prime would actually be the derivative of root x, which is x to the 1/2. We know that, right? So what is that? Again, it's an x to the n. So x to the n, rule 4, bring the power in front. So the power 1/2 comes in front of the x, and then you subtract 1 because it's n minus 1, so it's 1/2 minus 1. What is that? That is 1 over 2 x to the 1/2 minus 1 minus 1/2. Now in this course we're going to take the good habit to not leave answers with negative exponents. So that is actually 1 over 2, and we've seen that in the rules of exponents in the review video number 1. X to the minus 1/2 is 1 over x to the positive 1/2. Yes? So I can write this as one single fraction, 1 over 2 x to the 1/2, or 1 over 2 root x. Once again, if you did the limit definition on this guy, right? if you did the limit definition, you would get the root of x plus h minus the root of x over h. You would have to do the conjugate. It would take you like long, and you would get this in the end. So this is a much, much, much shorter way to get this. So before we go, a 5-second resume. So summary of today. What have we done today? We have moved forward into the rules of derivatives. Rule 1, the derivative of a constant is 0. Rule 2, the derivative of x alone is 1. Rule 3, a constant times x derivative is just the constant. And the latest, rule 4, the derivative of x to the n is now n, x to the n minus 1. In the next video, we will add on some rules to this short list, and we will actually build up a corpus of problems we can actually solve by completely bypassing the limit definition. I wish you well. I'll see you soon. Take care.